I think we can start the today's session. Today's session will be a problem solving session as usual. We have done for last 3 sessions. For now, today is for week 4 assignment we have, and today I have shared the screen for the week 4 assignment, and I'll be solving the following questions. So the first question is that at temperatures very small than Fermi temperature, which of the following statement is correct for the Fermi Dirac distribution function? Now if I write the Fermi Dirac distribution function, it gives me this thing, and pictorial representation of this function with respect to energy would be a function whose value is 1 for energies below a certain energy, say Fermi energy, and then let me take a different color. Value is 1 and then value is 0. Now when temperatures are very small than Fermi temperatures, now this is true for temperature is equal to 0 K, and for temperatures very smaller than Fermi temperatures, we can say that temperatures are closer to 0 Kelvin. Okay, now in this temperature range, what we have is the Fermi function is constant and then it becomes 0. So for the following option we have is the Fermi function is constant and nearly equals to 1. Option number 4th is correct in the following sense. Okay, now the second question we have is the energy dispersion relation of one-dimensional crystal is given by Ek is equal to sine square Ka by 2. Then what is the magnitude of group velocity? Now since Ek is given to us as sine square Ka by 2, and we know that group velocity expression is given by 1 by h cross dE by dk. What we do, we plug these values in. D by dk of sine square Ka by 2. Just differentiate sine square theta is 2 sine Ka by 2 cos Ka by 2 and A by 2. So finally what we have is A by 2h cross 2 sine Ka by 2 and cos Ka by 2. Now 2 sine Ka by 2 and cos Ka by 2 is nothing but 2 sine theta cos theta and nothing but sine 2 theta is 2 by h cross sine 2 theta would become sine Ka. Let me add a page to this point. I should add it here. Okay, now at zone edge, now what we are required is to find the group velocity of an electron at the zone edge. At zone edge, K is plus or minus pi by A. So if you plug these value here, our group velocity become A sine pi. Now sine pi becomes 0, therefore group velocity tends to 0 as V1 goes to the zone edges, and therefore the correct option would be group velocity is 0. Now there is another way of approaching this question, is that we have seen that these curves, energy dispersion curve follows this way. Okay, and this upward as the energy approaches the zone boundary, this has this type of curvature, and we know that at these points mass tends to infinity, and because mass is inversely proportional to the curvature, and if mass tends to infinity, the particle can't move and group velocity tends to 0. So both way one can do that. Okay. Now question number 3, let's do it. Consider a two-dimensional lattice with lattice constant A, and the radius of the Fermi circle which encloses the first Brillouin zone completely is. Now let's draw a reciprocal, a two-dimensional lattice. First a two-dimensional lattice. Now in two-dimensional lattice, this in reciprocal space, this lattice would be pi by A. So this, all these lengths, distance between the points is pi by A. Now let me take this point at the center and draw a Brillouin zone corresponding to it. Brillouin zone would be half of this distance. Okay. Then if I take this point, then half this point, perpendicular bisector of this distance, and then with this. And if I denote these points as, let's say, plus pi by A comma 0, and if I just say that this point is 0 0 because origin is our choice, and this point I say minus pi by A 0, and y-axis would become pi by A comma 2 pi by A, and this point would become as minus pi by A comma 2 pi by A. So now what we have is the following. This distance is pi by A, this distance is again pi by A. So if this, let's say this is A and this is B, so the vector that goes, the vector sum would be, this distance would be root 2 times pi by A, and what we are bound to find is the radius of the Fermi circle which encloses the first Brillouin zone. Now this distance is nothing but kf, because if you take a radius, if you take this distance and this as the center and draw a circle which encloses the first Brillouin zone completely, that radius have to be equal to kf equal to root 2 times pi by A. So the correct answer would be root 2 times pi by A. Let's go to the next one. Now this says that at temperatures very larger than Fermi temperature, which of the following statement is correct for Fermi Dirac distribution function? Now the condition that is given to us is temperature is very larger than TF. So when T is extremely large than TF, what we can assume that this is actually the high temperature limit or the classical limit, right? And since T is very large than TF, T is large than TF, but T is not infinity. Okay, so what also we can say here, that at these high temperatures lots of high energy states are occupied, that is energy would be much larger than EF. Okay, so what we can say here in this Fermi Dirac distribution function, E is the power E minus EF by kBT plus 1. Now when E becomes extremely larger than EF in this expression here, exponential becomes very big than 1. So one can neglect 1, and then one would be left with exponential minus of E minus EF divided by kBT. Now this is not an exact expression, this is an approximation, but one gets an idea that at temperatures very larger than Fermi temperature, the Fermi function actually goes as exponentially decay. So the correct answer would be the function is exponentially decaying at this temperature, because we are in classical limit, and in classical limit Fermi Dirac distribution approaches Maxwell-Boltzmann, where we have exponential decays. Now question number 5. Now in this question, what I found is that this question cannot be approached in a way that if the condition given is T approximately equal to TF. Rather than this way, one should have been given as energies equal to Fermi energy. Now if such condition is given, if such correction is made to the question, then we can try to answer the question as follows. Now as we have already found that Fermi function varies with energy in the way with energy is less than EF, one has a probability of occupancy 1 and 0 for the later part, and this is valid for T is equal to 0. Okay, now for T is very closer to say very closer to 0 Kelvin, then this Fermi function passes through half and then decays, so this function is still pretty sharp. It's not smooth, still pretty sharp, because this comes as this way and then goes as this. So what we are supposed to found here is the derivative of this Fermi Dirac distribution function with respect to temperature. We can say that at T equal to 0 Kelvin it is a delta function sort of, and then T very close to the 0 Kelvin and energy is very close to Fermi energy, this Fermi function drops extremely sharply. So Fermi function is sharply peaked at this temperature. This temperature means temperatures less than or I should say temperatures ratio to Fermi temperature is approximately 10⁻². Now in this regime of temperatures, the Fermi function distribution is sharply peaked. So the correct answer for the present question would be the function is sharply peaked at this temperature. Now we have another question which says that which of the following relations is true for the energy density of states of a three-dimensional electron gas. Now what we can do is density of states is the derivative of number of states with respect to energy, that is dN by dE, right? And just find the correct place. Yes, here it is. So let us take since we have to find for three-dimensional gas, let us draw it. Kx, Ky and Kz, and these are the individual K points along this line. Now what I can do, I can draw a general sphere of radius K. Okay, now in this sphere the smallest volume, I can say the smallest volume occupied by a single Y state, in fact single state, would be unit element along Ky multiplied by unit element along Kx multiplied by unit element along Kz, and these unit elements are in fact 2 pi by Lx 2 pi by Ly and 2 pi by Lz, following the inverse relationship between k and wavelength of the wave. So the smallest volume occupied will be, since we have a cube, is ABC. It becomes 8 pi cube Lx, Ly and Lz are actually these are actually the dimension of the specimen that we have taken. Now this specimen can be in the size of, say, microns or any other size which you are taken. So Lx, Ly and Lz is actually the physical volume. Multiplication of Lx and Y Lz is the physical volume of the specimen. So I'll denote this by capital V. So the smallest volume occupied by single state is actually given by 8 pi cube by V. And volume occupied by n states. We don't know what n is. Now for general n, we can assume a general k associated with it, and for a radius of for a sphere of radius k, one can find the volume to be 4 by 3 pi k cube. So n states will occupy a volume 4 by 3 pi k cube, and individual volume of the single state is 8 pi cube. So the number of states one can find is easily by dividing them. Number of states would be 4 pi k cube divided by 3 divided by 8 pi cube divided by the volume, and what we have here is V k cube divided by 6 pi square. So these are the number of states we have, right? But electrons have spin, and every state can accommodate 2 electrons, so we have to have twice the number of states. So every state can have 2 electrons in it, therefore total states would be twice of V k cube by 6 pi square, which is nothing but V k cube by 3 pi square. So now we have total number of states, and as I said, the density of states is derivative of number of states with respect to energy. Now to convert to find DOS, we need to differentiate the following expression with respect to energy, but we have k inside the bracket, so one can easily convert energy to k as h cross square k square by 2m, 2me by h cross square, total square root would be k. One can separate it in following fashion: 2m by h cross square half, and e half would be k. And since we require k cube here, what we'll do is cube both sides, so k cube value becomes this. After plugging in this value, V by 3 pi square can be taken out, and so I'll write it as separate. V by 3 pi square, first derivative of 2m by h cross square is called 3 by 2 into e raised power 3 by 2. V by 3 pi square into 2m by h cross square raised power 3 by 2, 3 by 2 times e raised power half are the number of density of states we have. 3 goes with 3, and we are left with V divided by 2 pi square, 2m by h cross square, 3 by 2. So density of states varies as e raised power half in 3 dimension. So in 3 dimension, density of states varies as e raised power half, and the following is the answer. Now we can follow the same strategy for calculating the density of states in a 2 dimension. Okay, now in a 2 dimension, in 2 dimensions, sphere which we considered above would be replaced by a circle. So, and volume would be replaced by area. Okay, so as in this above problem, we calculated the smallest volume occupied by single state. What we will do is we will calculate the smallest area occupied by a single state, and that would be nothing but, since we had 2 pi Lx, 2 pi Ly, 2 pi Lz as the volume, now what we will have is 2 pi by Lx into 2 pi by Ly. Let us take xy as the two dimensions we are talking about, and what we are left with is Lx and Ly, which counts to the physical area of the specimen which we are talking about. So 4 pi square divided by A is the smallest area occupied by a single state, and let us say the total area occupied by n states, which we found by, let's replace radius by general k vector, and area occupied by n states would be area is pi r square, so that would become pi k square. Fine. And total number of states would be nothing but pi k square divided by 4 pi square divided by A, which is nothing but A k square by 4 pi. And since we are talking about electrons, so let's double it, and then we take a derivative of it. A divided by 4 pi. So now I am talking about density of states as derivative of total number of states. Now k square, as we have found earlier, k was given by root 2me by h cross square. So since root 2me by h cross square is nothing but k, so k square would be 2me by h cross square. So one can plug directly 2me by h cross square. So 2 to 4 goes with here, and we are left with a by h cross square into first derivative of m is also there. First derivative with respect to energy is nothing but a constant, so we are left with am by h cross square, one has a pi. So density of states in case of 2 dimension is, since area is of the physical specimen is constant, mass of electrons is constant, pi and h cross square Planck's constant are constants, so dose in 2 dimension is a constant, or I can say dose varies as energy raised to power 0. So what we are left is density of states is constant for a 2-dimensional electron gas. Now proceeding further, the following question, question number, let's say 8, says that Fermi energy of a metal A is 4 times the Fermi energy of a metal B. So what we are given is Fermi energy of, say, metal A is 4 times Fermi energy of, say, metal B. What we are required is to find the electron density follows the relation. The electron density Na by Nb is equal to what? Okay, this is what we are required to find. First, now these Fermi energies are related to with kf, the Fermi wave vector, in the following fashion, and kf is related to the electron density as follows: 3n pi square raised to the power 1 by 3. Okay, now what I can do is I can plug these values there in these two equations, and what I found is as this. h cross square kf square divided by 2m for metal A is actually 4 times h cross square by 2m kf square for metal B. Okay, so and kf can further be replaced by 3n pi square raised to power 1 by 3. So what I have is h cross square by 2m. Kf square would mean 3n pi square raised to the power 2 by 3, and since I'm talking about metal A, I'll write n as a subscript of A is 4 times h cross square by 2m. Kf would become 3 times nb pi square raised to the power 2 by 3. Let's see, common things cancel up. 3 pi square also cancel from both sides. What we are left with is na raised to the power 2 by 3 is equal to 4 times nb raised to the power 2 by 3, or I can say na by nb the whole power 2 by 3 is nothing but equal to 4, which can be written as 2 raised to the power 2. So the exponents goes off. Na is equal to twice, or I can say na by nb 1 by 3 is twice, cubing both sides and multiplying the denominator to the right. Na becomes 8 times nb. So the electron density of metal A becomes 8 times electron density of metal B, which is the following answer. Okay, now our next question is as follows. The given Fermi energy for copper is given to us is 7 eV. So Fermi energy given is 7 eV. And what is the specific heat of copper in the units of joule per mole per Kelvin at room temperature 300 K? What we are given is temperature as 300 Kelvin. Now to convert electron volts into joule, what we can do is multiplied by the electronic charge, that is 10 to minus 19 coulomb. So Fermi energy in terms of joule becomes this quantity, and since we know that Fermi energy is related to Fermi temperature as kBTF, therefore kBTF would become EF by Boltzmann constant. One can find this calculation in 1.3, that is the value of Boltzmann constant minus 23. If one solves this, one would find 8.11 into 10 raised to the power 4 Kelvin. So this is our Fermi temperature, and heat capacity and the specific heat of the system is related to Fermi temperature in the following way. Cv is n times pi square by 2 ratio of the temperature which we are talking about at which the system is, ratio of temperature to Fermi temperature multiplied by the Boltzmann constant. Now since we have calculated all the values, we can plug these values in. N is moles, so 1 mole, 2 mole, or I should say the number of particles, and for 1 mole, since we are required to find per mole, I can plug in the Avogadro number multiplied by 3.14 square divided by 2. The temperature we are talking about is 300 Kelvin, and Fermi temperature which we have calculated just above is 8.1 times power 4 multiplied by the Boltzmann constant minus 23. And if one does the calculation, 23 goes with 23, 10 power 4 in the mid, this becomes 150, so approximately 6.022 multiplied by this would turn out to be 9.86 multiplied by 150 multiplied by 1.38 divided by 8.11 into 10 power 4. This approximately comes to be 0.15, and we are calculating the specific heat. So 0.15 is the specific heat of copper at room temperature in the units of, for sure, joule per mole per Kelvin. Now the next question, that is, we have what is the angle between the tangent to the energy dispersion curve and the zone boundary at the zone boundary. Now we know that the dispersion curves for EK dispersion curve behaves as if in this way, but due to the presence of potential, this curve breaks at the zone boundaries, and the way the curve approaches zone boundary is quadratically. So this curve I can draw a bit better as this, and this is the zone boundary we have. And the similar way, if I draw this correctly, so the energy dispersion curve approaches the zone boundary as parabolically. So at this zone boundary, at this point, the tangent to this curve is actually parallel to x-axis, and when tangent is parallel to x-axis, it strikes the zone boundary at 90 degrees. Okay, 90 degrees is nothing but pi by 2. Therefore, the angle between the tangent and the zone boundary is pi by 2, which is nothing but our option right here. Now this next question, 11th, that is, in a reduced zone scheme, the energy bands of a solid has k values in the range. In reduced zone scheme, one can bring all the other bands into a single band, into a single zone, and one would have a situation of this kind. You can have multiple bands going above. This is pi by a and minus pi by a. So actually what we have done is we have bring this part over here and this part over here. So in this reduced zone scheme, the k values lies in the range of minus pi by a and pi by a, and therefore our option is k lies between minus pi by a and pi by a. So in this way we have solved the assignment for week 4. Okay, I hope I have you understood the solutions. So if any one of the participants have any questions, one can unmute themselves and ask anything if you want to. I can see 2 participants in the present session.
Thank you, sir. May I have the solution of first one, that is problem number 1, please? Roll back the slides.
Sure. Yes.
So below that one, second I think.
Okay.
Okay, thank you, sir.
Okay. If other people doesn't have any questions or anything, I think we can conclude the present session, and we will meet next Tuesday at the same time, 7 p.m. for the assignment solutions for the next solutions for the assignment, that would be week 5.
Thank you very much, sir.
Thank you so much for joining the present session. I will be stopping this meeting, and you people can log out.